Hey, welcome back. And in this video, we are now going to start talking about convergence because we want to figure out whether a Taylor series converges or not. But we're not just going to be interested in whether the Taylor series converges, but we're going to be interested in if it converges to the function f of x that it represents. Okay, so now recall that if we look at the nth Taylor polynomial, it really is just a partial sum, right? It's an nth partial sum of the Taylor series. So in order to show that the Taylor series converges, we have to show that the sequence of partial sums, i.e. the Taylor polynomials, also converge. Now, there's something more. In order to show that it converges to a particular function, then we're also going to have to define a remainder. Okay, and so what we're going to do is the remainder r sub n of x is going to be defined as f of x minus Pn of x, where this represents the nth partial sum, or the nth Taylor polynomial, and this is the function that it represents. And so if the sequence of partial sums, in other words, the Taylor polynomials, right, the nth Taylor polynomials converges to f of x, then that would mean that all we would need to show is that the remainder is converges to 0. And to determine if r sub n converges to 0, we're going to introduce Taylor's theorem with remainder. Now, not only is this theorem useful in proving that the Taylor series converges to a related function or the related function, but it also allows us to quantify how well our Taylor polynomial approximates the function, just like before. We've used remainders before, right? So what we're going to do is we're going to look at the bound of the absolute value of the remainder. Okay, and to start off, we're going to look at r sub n. Okay, right, just do like before with other remainders, like for the, what was it? The other error bounds, we're looking for the maximum value, so we're going to also be looking for a maximum value for this one. So we want to see if r sub n is going to be bounded somehow, but let's see how we get there. So let's start with r sub 0. So r sub 0 is going to be f of x minus p0 of x. Okay, so that's going to be the remainder. And so p0 represents the 0th Taylor polynomial at a for a function f. And so this is going to equal f of x minus f of a, right? Because the zeroth Taylor polynomial is just f of a. Now here's the if the function is differentiable on the interval I containing a and x, then by the mean value theorem, then there has to exist a real number c between a and x such that this is true. What does the mean value theorem say? Well, that we would find a value c such that f of x minus f of a is equal to f of c prime, so f prime of c times x minus a. Okay, so that's from the mean value theorem. Okay, so far so good. So therefore, we can say that r of 0 is equal to f prime of c times x minus a. Okay, so that's for r0. Now, if we use the mean value theorem in a similar argument, we can show that if f is n times differentiable on an interval I containing both a and x, then we can also show that r sub n satisfies the following. That r sub n is going to equal this is going to be f n plus 1 of c over n plus 1 quantity factorial, and this is going to be x minus a to the n plus 1. Okay, so now notice that c is in the numerator here. Okay, it's important to realize that c is used in the numerator. Also that c is between x and a. It's not equal to a. Okay, so this is f of c, not equal to a. Okay, so it's distinct from a. Okay. So now what we're going to use this formula allows us to get a bound on the remainder r sub n. Okay, now if we happen to know that the absolute value of this, if we know that if we take that expression actually if that is bounded, right? if it's bounded by some real number on the interval I, then we can replace that with that real number in this formula. So if we can show that this is bounded by some real number m, like before in the trapezoidal other remainders theorems that we've used, so we could say that this is less than or equal to some real number m, then we can replace this with m. Okay, and now here's the thing. We're also, remember, we're going to take the absolute value of the remainder. So that would mean that the absolute value of r sub n, oops, let me go back to this. So that would mean that the absolute value of r sub n of x is going to be less than or equal to m over n plus 1 factorial. Now again, these are just real numbers, so we can drop the absolute value signs on these, but not on this one. So it would be the absolute value of x minus a to the n plus 1 power. And that's going to be for all x in the interval I. Okay, and that's where we're at. And so this brings us to the Taylor theorem, the remainder theorem. Okay, and that's next. So we'll introduce the theorem and then we'll do some examples. See you then.